Light is one of the first things we notice when we wake up, and one of the last sensations to fade when we close our eyes. It arrives quietly, fills a room, reflects from surfaces, and carries information to our senses. We use it constantly, yet rarely pause to ask what it actually is or what it is made of. Tonight, we'll explore that simple question. What are photons actually made of? Not as a puzzle to solve quickly, but as something to understand slowly, step by step, with calm attention. Welcome to AstraFlow. Here, science drifts like starlight, and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing soften, and your mind settle into quiet understanding. If you're listening from somewhere familiar or far away, you're welcome to share that in the comments. If this kind of slow, science-led exploration helps you rest, a gentle like or subscription helps support the channel and keeps these quiet journeys going. Now, let's begin and explore the science of what photons are actually made of. When we hear the word photon, it's easy to imagine something small and bright, perhaps like a tiny grain of light moving through space. This image feels natural because our everyday experience is built around solid objects. We understand things by picturing their shape, their size, and what they're made from. But photons do not fit neatly into that way of thinking. In physics, photons are defined as the fundamental units of light. They are not pieces broken off from something larger, and they are not built from smaller components. According to everything we currently know, a photon is an elementary entity. That means it does not have internal structure in the way atoms or molecules do. There are no smaller parts inside it waiting to be discovered. This can feel unsatisfying at first. When we ask what something is made of, we usually expect a list of ingredients. Wood is made of fibers, metal is made of atoms, atoms are made of particles. But with photons, the chain ends. They are not made of something else. Instead, they are expressions of something more fundamental. To understand this, we need to gently shift how we think about stuff in the universe. Not everything that exists is a solid object. Energy, motion, temperature, and fields are all real physical things, even though they are not made of matter. Photons belong to this category. They are real and measurable, but not material in the usual sense. A photon carries energy and momentum, even though it has no rest mass. This is why light can warm your skin, power a solar panel, or push against objects in space. These effects are subtle, but they are real. The absence of mass does not mean the absence of physical presence. Another important feature of photons is that they always move at the same speed in a vacuum, the speed of light. They do not slow down, and they cannot be at rest. This constant motion is not a choice or a behavior. It is a direct result of what photons are. Rather than being made of substance, photons are better understood as events or excitations. They arise when energy is exchanged in specific ways, and they disappear when that energy is absorbed. They are moments of interaction, not tiny objects travelling like beads through space. As we move forward, we'll look more closely at how photons emerge, how they behave, and how they connect light, energy, and fields into a single coherent picture. For now, it's enough to rest with this idea. Photons are not things built from parts. They are fundamental expressions of how energy moves through the universe. Before we can understand what photons are made of, it helps to slow down and clarify what we mean when we say the word light. In everyday language, light is something that lets us see. It brightens a room, reflects off surfaces, and creates shadows. But in science, light has a more precise meaning. Light is a form of electromagnetic radiation. This sounds technical, but the idea itself is gentle and concrete. Electromagnetic radiation is energy that travels through space in a structured way, carried by electric and magnetic effects that are linked together. Light is not unique in this respect. It belongs to a much larger family of related phenomena: radio waves, microwaves, infrared radiation, visible light, ultraviolet light, X-rays and gamma rays are all part of the same spectrum. They differ only in energy and wavelength. The light your eyes detect is just a small, narrow slice of this continuous range. What connects all of these forms of radiation is that they can all be described using photons. A photon is the smallest measurable unit of electromagnetic energy. It is not a fragment chipped off a wave. It is the basic way energy is exchanged in electromagnetic interactions. This is where the idea of light becomes subtle. Light behaves like a wave when it travels. It spreads out, interferes with itself, and bends around obstacles. But when light interacts with matter, when it is emitted, absorbed, or detected, it behaves in discrete steps. These steps are photons. So light is not either a wave or a stream of particles. It is a physical process that shows different aspects depending on how it is observed. The wave description tells us how light moves through space. The photon description tells us how light exchanges energy. This dual description is not a flaw or a mystery to be solved later. It is simply how nature behaves at very small scales. Light does not need to choose one identity. Our models adjust depending on what we are measuring. When a lamp turns on, atoms inside it release energy. That energy does not flow out smoothly like water from a tap. Instead, it is released in tiny, specific amounts. Each of those amounts is a photon. When those photons reach your eyes, they are absorbed by specialized cells, again in discrete events. Vision itself happens one photon at a time. This tells us something important. Light is not a substance filling space like fog. It is a transfer of energy between systems. The photon is the bookkeeping unit that keeps track of how much energy moves and where. Because photons are tied to energy rather than matter, they behave differently from objects we're used to. They have no fixed size. They do not occupy space the way a grain of sand does. Asking how big a photon is not always a meaningful question. What matters is its energy, its direction, and how it interacts. Understanding light in this way helps clear away a common misunderstanding. Photons are not tiny glowing balls flying through empty darkness. That picture can be useful at first, but it eventually gets in the way. Light is better understood as activity, not substance. As we continue, we'll focus more closely on photons themselves, not just as units of light, but as fundamental elements of how the universe handles energy. For now, you can rest with this steady idea. Light is a physical process, and photons are how that process becomes measurable. Now that we've clarified what light is, we can narrow our attention to photons themselves. A photon is often described as a particle of light, but that phrase can be misleading if taken too literally. It's more accurate to think of a photon as a unit, a smallest countable amount, of electromagnetic energy. In physics, many quantities are continuous at large scales but discrete at small ones. Water flows smoothly in a river, yet it is made of individual molecules. Heat feels like a continuous warmth, yet it moves through matter in quantized exchanges of energy. Light follows the same pattern. At everyday scales, it behaves like a smooth wave. At the scale of interactions, it comes in individual packets. Those packets are photons. A photon is defined by a few key properties: It has a specific amount of energy which depends on its frequency. Higher frequency light, like blue or ultraviolet, corresponds to higher energy photons. Lower frequency light, like red or infrared, corresponds to lower energy photons. This relationship is precise and consistent across all situations we've measured. Importantly, photons are not all identical in energy. There is no single standard photon. Instead, photons form a continuous range, each one tied to a specific frequency of electromagnetic radiation. What unites them is not their energy level, but their role as carriers of electromagnetic energy. Calling photons particles can create the impression that they are small solid objects. But photons do not have volume or shape in the usual sense. They cannot be held, stacked, or confined like grains of matter. The word particle is used because photons interact in localized countable events. A detector either absorbs a photon or it doesn't. There is no half absorption. This discreteness is one of the reasons photons were proposed in the first place. Early experiments showed that light transfers energy in fixed amounts, not in smooth fractions. For example, in the photoelectric effect, light shining on a metal surface ejects electrons only if the photons have enough energy. Increasing brightness increases the number of electrons released, not their energy. That behavior makes sense if light arrives in individual energy packets. Another important feature of photons is that they are always created and destroyed in interactions. A photon does not slowly lose energy as it travels through empty space. It is emitted with a certain energy, and, unless it interacts with something, it keeps that energy. When it is absorbed, it transfers all of it at once. This makes photons very different from objects that wear down or break apart. A photon does not age. It does not decay. It simply exists as long as it is not interacting. Because photons are units of interaction, they are best understood in terms of processes. An atom emits a photon, a molecule absorbs a photon, an eye detects a photon. In each case, the photon marks a discrete exchange of energy between systems. This perspective helps answer part of our original question. Photons are not made of smaller pieces. They are defined by how much energy they carry and how they interact. Their substance, if we can use that word at all, is energy structured by the electromagnetic field. As we move on, we'll look at why photons are considered fundamental and what it means to say that something has no internal structure. For now, let the idea settle gently. Photons are not objects in space so much as events in the flow of energy. At this point, it's natural to return to the central question and press it a little more firmly. If photons carry energy, if they behave in consistent ways, and if they interact with matter, then why do we say they're not made of anything smaller? What does it really mean in science to call something fundamental? In physics, a fundamental entity is one that shows no evidence of internal structure. This doesn't mean we assume it has no structure because we haven't looked closely enough. It means that after extensive observation, experimentation, and measurement, there is no sign that it can be divided into components. Photons fall into this category. When scientists study matter, they often do so by smashing particles together at high energies. If a particle is made of smaller pieces, those pieces tend to reveal themselves under enough energy. This is how atoms were found to contain electrons and nuclei, and how protons were found to contain quarks. Photons behave differently. No matter how carefully we test them, photons do not break into parts. This is not because photons are especially durable, but because there is nothing inside them to break apart. They do not contain subparticles orbiting or vibrating internally. There is no smaller photon hidden within a larger one. As far as current physics can tell, the photon is already at the most basic level. This idea can feel abstract because we are used to thinking of things as built from pieces. Even liquids and gases, which feel smooth and continuous, are made of molecules. But nature does not require everything to follow this pattern. Some things exist as irreducible units, defined not by their composition but by their role. For photons, that role is to mediate electromagnetic interactions. They are how electric and magnetic effects propagate and exchange energy. In modern physics, this role is described using fields. The electromagnetic field exists everywhere in space. A photon is a specific excitation or disturbance of that field. This is a subtle but important shift in thinking. Instead of asking, what is the photon made of? It becomes more accurate to ask, what process does the photon represent? The answer is not a material substance, but a change in the state of a field. Fields are not mathematical inventions layered on top of reality. They are measurable physical entities. Electric and magnetic fields exert forces, store energy, and respond to changes. The electromagnetic field is as real as matter, even though it is not made of atoms. From this perspective, a photon is similar to a ripple on a surface, but without a surface underneath. It is a localized change in a field that carries energy and momentum. There is no smaller ripple inside it, because the ripple itself is the basic event. It's also important to notice what scientists do not say. They do not say photons are made of pure energy in a vague or mystical sense. Energy is a property, not a substance. Photons carry energy, but they are not made of energy in the way a chair is made of wood. Instead, photons are defined by their measurable properties: energy, momentum, polarization, and how they interact. These properties are sufficient to fully describe their behavior. There's no missing ingredient that needs to be filled in. As we continue, we'll look more closely at how photons can have energy and momentum without mass, and why this does not violate the rules of physics. For now, you can rest with a clear and grounded idea. Photons are not built from smaller parts because they are already as simple as nature allows. When people first hear that photons have no mass, it can sound as if they are barely real, or somehow less physical than solid objects. In everyday experience, mass is closely tied to existence. Things that have weight feel real. Things that don't are easy to overlook. But in physics, mass is only one of many properties an entity can have. Photons have no rest mass. This means that if you could somehow try to hold a photon still, it would not have mass in the usual sense. But photons cannot be held still. They always move at the speed of light in a vacuum. Their massless nature and their constant speed are deeply connected. Even without mass, photons carry energy. This energy is not abstract. It can heat objects, trigger chemical reactions, and move electric charges. When sunlight warms your skin, it is because photons transfer energy to the molecules in your body. When plants grow, it is because photons drive the chemical steps of photosynthesis. These effects are direct and measurable. Photons also carry momentum. Momentum is usually associated with moving objects that have mass, like a rolling ball or a flowing river. But momentum is more general than that. It depends on energy and motion, not just mass. Because photons carry momentum, they can exert pressure. This effect is very small in everyday situations, but it is real. Light can push on surfaces. In space, where there is very little resistance, this pressure becomes noticeable. Solar sails, for example, use the momentum of sunlight to gently accelerate spacecraft. The force is weak, but it accumulates over time. The fact that photons have momentum without mass may seem strange, but it fits naturally within the framework of modern physics. Energy and momentum are linked through well-tested equations. For photons, energy and momentum are related directly to frequency and wavelength. Because photons have no mass, they respond differently to gravity than massive objects do. They do not slow down as they move through space. Instead, gravity bends their path. Light passing near a massive object curves, not because it is pulled like a falling stone, but because space-time itself is curved. Photons follow those curves. This behavior has been observed many times, from starlight bending around the sun to distant galaxies acting like lenses. These observations reinforce the idea that photons are fully part of the physical universe, even though they are not made of matter. Another important consequence of being massless is stability. Photons do not decay on their own. They do not wear out or lose energy as they travel through empty space. A photon emitted billions of years ago can still arrive today with its energy intact, aside from changes due to cosmic expansion. This constancy makes photons reliable messengers. They carry information across vast distances without changing their internal state. That reliability is one reason light is such a powerful tool in astronomy and measurement. So when we say photons are massless, we are not saying they are nothing. We are saying they are different. They are carriers of energy and momentum that do not require mass to exist or to act. Their physical influence is quiet but persistent. As we move forward, we'll look more closely at how photons can carry energy without substance, and what that tells us about the nature of physical reality. For now, it's enough to let this settle gently. Mass is not the same as reality, and photons are fully real. By now we've seen that photons carry energy and momentum without having mass. This naturally leads to a quieter, deeper idea that takes some time to settle. Energy does not always need a material substance to exist or to move. In daily life, energy is almost always tied to something solid. A moving car has kinetic energy. A warm cup of tea has thermal energy stored in its molecules. A stretched spring holds potential energy because of its shape. In all of these cases, energy feels inseparable from matter. But physics shows us that this is not always true. Energy is a property of physical systems, not a material ingredient. It describes the ability to cause change, to do work, or to produce motion. Photons are one of the clearest examples of energy existing and travelling independently of matter. When a photon moves through empty space, there is no object carrying it along like a container. There is no substance flowing from one place to another. Instead, energy is being transported through the electromagnetic field itself. The field is the physical structure that allows this transfer to happen. This can be difficult to picture because we don't have everyday sensory experience of fields. But fields are not abstract ideas. An electric field can push charges. A magnetic field can move a compass needle. The electromagnetic field can store energy and release it in precise amounts. A photon is one such release. Think of it not as something inside the field, but as something the field does. When conditions are right, the field changes in a specific, quantized way. That change propagates through space. That propagation is what we call a photon. This is why asking what a photon is made of can quietly miss the point. A photon is not a container holding energy. It is the energy organized in a specific, measurable pattern. There is no underlying material that needs to be peeled back. When a photon is absorbed, nothing material arrives and settles into the absorbing object. Instead, The electromagnetic field transfers energy to electrons or atoms. The photon as a distinct unit no longer exists. The energy continues on in another form, as motion, heat, or chemical change. This transfer is always precise. A photon's energy is not smeared out or partially absorbed. It is delivered in full. This precision is one of the defining features of quantum behavior and one of the reasons photons are so important in science and technology. It also explains why photons do not gradually fade as they travel. In empty space, there is nothing for them to interact with. Without interaction, there is no mechanism for energy loss. The photon continues unchanged until it meets something that can absorb it. This view helps unify many ideas we've already touched on. Light is not a stream of material particles. It is a flow of energy structured by a field. Photons are the smallest indivisible units of that flow. As we continue, we'll turn our attention to one of the most distinctive properties of photons, their constant speed. Understanding why photons always move at the speed of light will deepen this picture and further clarify what kind of entities they are. For now, you can let this idea rest gently in the background. Energy does not always need substance, and photons are living proof of that quiet fact. One of the most distinctive features of photons is that they always travel at the same speed when moving through empty space. This speed, often called the speed of light, is not just a high number. It is a fundamental feature of how the universe is structured. No matter how a photon is created, no matter how much energy it carries, and no matter where it is travelling, its speed in a vacuum is always the same. This is not true for objects with mass. Cars, planets, and even atoms can move faster or slower, depending on how much energy they have. Photons cannot. This constancy tells us something important about what photons are. Their speed is not the result of being pushed or accelerated. It is not something they gradually reach. From the moment a photon exists, it moves at that speed. There's no state in which a photon is at rest. The reason for this lies in the connection between mass, energy, and motion. Objects with mass resist acceleration. They can be still or they can move at different speeds. Photons have the rest mass, and this removes that flexibility. In the structure of physical laws, massless entities must move at a fixed speed. This is not a rule imposed afterward. It emerges naturally from the way space and time are linked. In modern physics, space and time form a single combined structure, often called space-time. The speed of light acts as a kind of conversion factor between space and time, setting the scale at which cause and effect can propagate. Photons sit right on this boundary. They are the fastest possible carriers of information and energy. Nothing can outrun them, not because they are powerful or forceful, but because the universe does not allow anything to go faster. This also explains why photons do not experience time in the way massive objects do. From the photon's perspective, and if we can speak that way carefully, there is no passage of time between emission and absorption. The journey happens without aging or delay. This is not something we need to imagine vividly. It is simply a consequence of the mathematics that describes motion at light speed. When photons pass through materials like air, glass, or water, they appear to slow down. But this is a collective effect. The photons are absorbed and re-emitted, or their interactions with atoms delay their progress. Between these interactions, they still move at their characteristic speed. This constant speed reinforces the idea that photons are not objects drifting through space. They are closer to signals, consistent rule-bound processes that connect events. An atom emits a photon. Later, another system absorbs it. The photon is the link between those events, travelling at a speed that reflects the deep structure of space-time itself. Understanding this helps us move away from the idea of photons as tiny projectiles. Instead, we can see them as fundamental messengers, moving in the only way massless energy can move. As we go on, we'll look beneath this motion and explore the electromagnetic fields that make photons possible in the first place. For now, you can rest with this steady fact. The speed of light is not just fast, it is revealing. To understand what photons are at the deepest practical level, we need to spend some quiet time with the idea of fields, not as equations or diagrams, but as real physical structures that exist everywhere, even where there seems to be nothing at all. An electromagnetic field is a physical condition of space that determines how electric charges and magnets behave. If you place an electric charge somewhere, it creates an electric field around it. If you move a magnet, it creates a magnetic field. These fields are not just convenient descriptions. They exert forces, store energy, and respond to changes. They can be measured directly. What makes the electromagnetic field special is that electric and magnetic effects are not separate. They are two aspects of the same field, intertwined. A changing electric field produces a magnetic field. A changing magnetic field produces an electric field. This self-sustaining relationship allows energy to propagate through space. That propagation is light. From this perspective, a photon is not an object travelling through a field. It is a specific, organised change of the electromagnetic field itself. When energy is added to the field in the right way, a photon emerges as a travelling excitation. This is a quiet but profound shift in understanding. Instead of asking what substance a photon is made of, we recognise that the electromagnetic field is the underlying physical reality. The photon is what happens when that field changes in a discrete quantized way. Fields exist everywhere, even in regions we call empty space. There does not need to be matter present for the electromagnetic field to exist. This is why light can travel through the vacuum between stars and galaxies. The field is already there, ready to carry energy. When an atom emits a photon, it is not throwing out a tiny object, it is transferring energy into the electromagnetic field. That energy organizes itself into a stable, traveling pattern. That pattern moves outward, carrying energy and momentum until it interacts with something else. When a photon is absorbed, the process reverses. Energy moves from the field into matter. The field relaxes. The photon, as a distinct excitation, is gone. Nothing material has travelled from one place to another. What has travelled is influence. This way of thinking helps resolve many earlier confusions. It explains why photons have no internal structure. They are not built, they arise. It explains why they have no mass. They are not objects resisting motion. They are patterns of motion within a field. It also explains why photons are all fundamentally similar, even though their energies differ. The electromagnetic field is the same everywhere. Photons are different expressions of that same field, distinguished only by how much energy they carry and how they are oriented. As we continue, we'll explore how these field excitations can behave like waves, spreading and interfering, even though they're exchanged in discrete units. For now, let this idea settle gently. Photons are what the electromagnetic field does when energy moves. Now that we've grounded ourselves in the idea of electromagnetic fields, we can take a calm step forward and look at how photons relate to vibration. This word is familiar from sound, from strings, from anything that oscillates. In physics, vibration simply means a repeating change over time. No metaphor is required. The electromagnetic field can vibrate. When it does, those vibrations can travel through space. A photon is one such vibration. Not a shaking of matter, but a structured oscillation of electric and magnetic components of the field. In this oscillation, the electric part of the field rises and falls in strength, while the magnetic part does the same, oriented at right angles. These changes are synchronized. As one varies, the other follows. Together they form a self-sustaining pattern that moves forward through space. This movement does not require anything to push it along. The field's own structure allows the oscillation to propagate. This is why light can travel through a vacuum. There is no medium being shaken. The field itself is what is changing. When we describe light as a wave, this is what we mean. We're describing the continuous, smooth variation of the electromagnetic field as it moves. The wavelength tells us how far the pattern repeats in space. The frequency tells us how fast it repeats in time. These two quantities determine the energy of the photon. Higher frequency vibrations correspond to higher energy photons. Lower frequency vibrations correspond to lower energy photons. This relationship is exact and unbroken across the entire electromagnetic spectrum. At this point, it's important to be precise without becoming abstract. The vibration is not something happening to the photon. The vibration is the photon. There is no underlying object being shaken. There is only the field changing in a specific quantized way. This is why photons do not have edges, surfaces, or internal structure. They are defined entirely by how the field behaves. Their identity is dynamic, not material. You might notice that this description feels smoother and more continuous than earlier descriptions of photons as discrete units. This is not a contradiction. It reflects the dual nature of how we describe light. When light travels, the wave picture is often the most useful. When light interacts, the photon picture becomes essential. Both descriptions are accurate. They highlight different aspects of the same physical reality. The electromagnetic field does not switch between being a wave and being a particle. Our language switches depending on what we are observing. This way of understanding light also explains why photons can spread out, interfere with one another, and pass through narrow openings in surprising ways. These behaviors follow naturally from the mathematics of waves. Nothing extra needs to be added. As we move on, we'll look more closely at how photons can still behave like particles during interactions, even though they are fundamentally field vibrations. For now, you can let this idea rest quietly. Light is a vibration of fields, structured, precise, and real. With the idea of light as a vibration of fields settled gently in place, we can now focus on how photons behave as waves when they move through space. This behavior is not an added feature or a special case. It is a direct consequence of the field-based nature of light. When photons travel, they do not move along a single narrow line like a tiny projectile. Instead, the electromagnetic field vibration spreads out. It occupies a region of space. This spreading is why light can illuminate an entire room from a single source and why it does not cast perfectly sharp shadows. One of the most well-known wave behaviors of light is interference. When two light waves overlap, their field vibrations combine. In some places, they reinforce each other, creating brighter regions. In other places, they cancel out, creating darkness. This pattern emerges naturally from the mathematics of waves and has been observed countless times. What's important here is that this interference happens even when light is extremely faint. Experiments show that if photons are sent one at a time through an arrangement that allows interference, the pattern still builds up gradually. Each photon contributes a single point, but over time the wave-like structure appears. This tells us something subtle. The wave behavior is not the result of photons interacting with each other. It is built into how each photon relates to the electromagnetic field and to the space it moves through. Another wave behavior is diffraction. When light passes through a narrow opening around an edge, it spreads out instead of continuing in a straight line. This spreading is predictable and depends on the wavelength of the light. Shorter wavelengths spread less, longer wavelengths spread more. Diffraction shows us that photons do not have a precise, sharply defined path in the way a thrown object does. Instead, their behavior is described in terms of probabilities. The electromagnetic field vibration defines whether photon can be detected, not a single track it must follow. This does not mean photons are vague or poorly defined. It means their behavior is governed by different rules than those of everyday objects. Those rules are consistent and precise, even if they challenge intuition. It's also important to note what wave behavior does not imply. It does not mean photons smear out into continuous energy. Detection always happens in discrete events. A sensor records a click. A molecule absorbs a specific amount of energy. The wave description tells us how likely those events are to occur in different places. In this way, the wave behavior of photons sets the stage, and the particle-like interaction provides the outcome. The field vibration shapes the possibilities. The photon defines the event. Understanding this balance helps prevent confusion. Photons are not sometimes waves and sometimes particles depending on their mood or environment. They are quantum entities whose behavior requires both descriptions to be complete. As we continue, we'll turn our attention to the other side of this picture, how photons behave during interactions and why those interactions are always discrete. For now, you can let this idea settle softly. Photons move like waves, even though they arrive like points. After spending time with the wave behavior of light, it's important to slow down and look just as carefully at the other side of photon behavior, how photons act during interactions. This is where the idea of photons as discrete units becomes essential. Whenever light interacts with matter, it does so in individual events. An atom absorbs a photon, a molecule emits a photon, a sensor detects a photon. These interactions never happen in fractions. There is no such thing as half a photon being absorbed. The exchange is always complete. This discreteness is not a limitation of our instruments, it is a property of nature itself. No matter how faint the light source is, detection always occurs in whole units. You can reduce the number of photons, but you cannot divide one. This particle-like behavior is most obvious when we look at how light transfers energy. If photons were spread out bits of energy, we would expect energy to trickle gradually into matter, but that is not what happens. Instead, energy arrives in precise packets, each one corresponding to a single photon. This is why certain processes have sharp thresholds. For example, an electron in an atom can only move to a higher energy state if it absorbs a photon with exactly the right amount of energy. If the photon's energy is too low, nothing happens. No matter how long you wait, the electron will not partially climb the energy ladder. This behavior makes sense if photons are indivisible units. The atom either receives the full packet of energy or receives nothing at all. It's also worth noticing that this particle behavior appears only at the moment of interaction. While a photon is traveling freely through space, the wave description works extremely well. But when it interacts with matter, the outcome is always localized. The energy ends up in one place, at one time. This does not mean the photon suddenly turns into a tiny object just before impact. It means that the laws governing interactions are quantized. The electromagnetic field exchanges energy in fixed units, and those units define the photon. From this perspective, particle behavior does not imply solid structure. It implies countability. It means events can be counted, outcomes are distinct, and energy transfer is precise. This helps clarify why photons are sometimes called particles, even though they lack mass, size, and shape. The word particle is doing a specific job. It tells us that interactions happen in discrete steps, not continuously. Understanding this helps dissolve a common confusion. Photons do not switch identities. They are not sometimes waves and sometimes particles in the everyday sense of those words. Instead, they are quantum entities whose motion is best described by waves and whose interactions are best described by particles. Both descriptions are accurate. Neither is complete on its own. As we move on, we'll explore why photons are so hard to picture intuitively and why our everyday concepts struggle at these scales. For now, you can let this rest gently. Photons arrive all at once, even when they travel as waves. By now, you may notice a quiet tension in how photons are described. They move like waves, spread out and interfere. Yet when they interact, they arrive in single, indivisible events. This combination can feel uncomfortable, not because it is unclear, but because it does not match the kinds of things we experience in everyday life. Our intuition is shaped by objects that have size, shape, and substance. We're used to things being either spread out, like water or air, or localized, like stones or tools. Photons do not fit cleanly into either category. They are not extended substances, and they are not compact objects. This is why photons are hard to picture. Any mental image we choose will emphasize one aspect and hide another. If we imagine photons as tiny particles, we lose their wave behavior. If we imagine them as waves, we lose the discreteness of their interactions. The difficulty is not a failure of explanation. It is a limit of visual imagination. Physics does not require us to picture photons correctly in order to describe them accurately. Instead, it provides mathematical structures that predict outcomes with extraordinary precision. These structures do not resemble familiar objects, and that is acceptable. Nature is not obligated to fit human intuition. It helps to remember that many things we understand well are also hard to picture. We cannot truly picture curved space-time, electric fields filling space, or probabilities shaping outcomes. Yet these concepts are grounded in measurement and experiment. Photons belong in this same category. Another reason photons resist clear imagery is that they are defined by relationships rather than contents. A photon is defined by how much energy it carries, how it is polarized, and how it interacts. There is no hidden interior to imagine. There is no surface to draw. When physicists talk about photons, they often rely on diagrams, equations, or simplified pictures. These are tools, not literal depictions. Each tool highlights one aspect as behavior and ignores others. Used carefully, they are helpful. Taken too literally, they become misleading. This is why good explanations often change perspective depending on context. When discussing light traveling through space, wave language dominates. When discussing light hitting a detector, particle language becomes essential. Neither description replaces the other. Understanding photons, then, is less about forming a perfect image and more about becoming comfortable with multiple complementary descriptions. This comfort grows slowly. It does not require effort or strain. It simply comes from letting go of the need for a single picture that explains everything at once. As we continue, we'll move from description to process, looking at how photons are created in the first place. For now, it's enough to rest with this idea. Photons are hard to picture because they are not objects like the ones we evolved to understand. To understand photons more fully, it helps to follow one from its beginning. Photons are not permanent residents of the universe. They come into existence through specific physical processes, and those processes are precise and well understood. One of the most common ways photons are created is through atomic emission. Atoms contain electrons that occupy specific energy levels. These levels are not continuous. An electron cannot sit halfway between them. It must occupy one level or another. When an atom gains energy through heat, electricity, or radiation, one of its electrons may move to a higher energy level. This state is often temporary. The electron naturally tends to return to a lower energy state, one that is more stable. When this happens, the excess energy must go somewhere. It cannot disappear. Instead, it is released into the electromagnetic field. That release takes the form of a photon. The energy of the emitted photon is exactly equal to the difference between the two energy levels involved. No more, no less. This is why atoms produce very specific colors of light. Each color corresponds to a specific photon energy. This process does not involve electrons throwing photons out like objects. Nothing is launched or expelled. Instead, the electromagnetic field reorganizes itself as energy is transferred from the atom into the field. Photon emission can also occur in other ways. Accelerated electric charges can produce photons. This is how radio antennas work. Changes in electric currents create changes in the electromagnetic field, which propagate outward as photons across a range of energies. In hot objects, many atoms and molecules are constantly gaining and losing energy. This leads to a continuous emission of photons across a range of frequencies. This is called thermal radiation. The glow of a heated metal or the warmth from your body are both examples. In all of these cases, the underlying idea is the same. A photon is created when energy moves from matter into the electromagnetic field in a discrete, organized way. There is no assembly process. There are no components brought together. The photon comes into existence fully formed, defined by its energy, direction, and polarization. This view reinforces what we've already learned. Photons are not objects constructed from pieces. They're events that occur when energy changes form. As we continue, we'll follow photons to the end of their journey and look at what happens when they are absorbed. For now, you can let this idea settle gently. Photons are born from transitions, not built from parts. Just as photons are created through precise physical processes, they also come to an end in equally precise ways. Photons do not slowly fade out or crumble as they move. They disappear only when they interact, and when they do, the process is exact and complete. Absorption is the most common way a photon ceases to exist as a photon. This happens when the energy carried by the photon is transferred into matter. The photon is not broken apart. It is not weakened. It is fully absorbed in a single event. At the atomic level, absorption mirrors emission. An electron in an atom can absorb a photon only if the photon's energy matches the difference between two allowed energy levels. If the energy does not match, the photon passes by without effect. This selectivity is one reason matter has distinct colors and transparency properties. When absorption occurs, the energy of the photon becomes energy of the atom or molecule. The electron moves to a higher energy state. That energy may later be released again as another photon converted into heat or used to drive a chemical reaction. The original photon, however, is gone. This all-or-nothing nature of absorption reinforces the idea that photons are indivisible units. There is no gradual soaking up of light. A molecule does not take a sip of energy from a passing photon. It either absorbs the entire photon or does nothing at all. Absorption also explains why materials appear opaque, transparent, or reflective. In opaque materials, photons are readily absorbed, transferring their energy into the material. In transparent materials, photons pass through with little interaction. In reflective materials, photons are absorbed and re-emitted in a way that sends them back outward. Even in reflection, the original photon does not bounce like a ball. The interaction involves absorption followed by emission. The outgoing photon may have the same energy as the incoming one, but it is a new event, not the same photon changing direction. This perspective helps clarify a subtle point. Photons do not travel from a source to a detector as tiny objects that remain intact from beginning to end. They exist as long as they are not interacting. When interaction occurs, the energy is transferred, and the photon as a distinct entity ends. Understanding absorption completes the basic life cycle of a photon. It is created when energy enters the electromagnetic field. It travels as a stable excitation. It disappears when its energy is transferred elsewhere. As we move forward, we'll see how the energy of photons relates directly to color and perception, connecting these abstract processes to everyday experience. For now, let this rest quietly. Photons end not by wearing out, but by giving everything they have in a single moment. With emission and absorption in mind, we can now connect photons to one of the most familiar experiences we have with light: color. Color feels subjective and sensory, but beneath that experience is a very direct physical relationship between photons and energy. Each photon carries a specific amount of energy. This energy is tied to its frequency, which is how quickly the electromagnetic field oscillates. Higher frequency photons carry more energy. Lower frequency photons carry less. Color is how our visual system interprets these differences. Photons with lower energies are associated with red light. As energy increases, color shifts through orange, yellow, green, blue, and violet. Beyond violet, photon energies continue to increase, but our eyes can no longer detect them. Those photons are still real. They simply fall outside the range our biology responds to. It's important to notice that color is not a property of photons alone. A photon does not carry a label saying blue or red. Color emerges from an interaction between photons and the cells in our eyes. The same photon energy that looks blue to a human would be invisible to a creature with a different visual system. Inside the eye, specialized cells absorb photons and respond differently depending on the photon's energy. These responses are combined and interpreted by the brain as color. The physical process is discrete, one photon absorbed at a time, but the experience feels smooth and continuous. This explains why color perception can change with lighting conditions. The same object can look different at sunrise, midday, or sunset. The photons illuminating it have different energy distributions, and the material absorbs and reflects some energies more than others. It also explains why objects have characteristic colors. A leaf appears green because its molecules absorb photons of certain energies and reflect others. The reflected photons reach your eyes, where they are absorbed again and translated into perception. At no point does color exist as a physical substance traveling through space. What travels are photons with specific energies. Colour is the interpretation that happens when those photons interact with a biological system. This understanding gently reinforces everything we've learned so far. Photons are defined by energy and interaction, not by material makeup. Their properties are precise and measurable, but their meaning depends on context. As we continue, we'll move beyond visible light and explore the vast range of photons that surround us but never reach our eyes. For now, you can let this idea settle softly. Color is energy made visible by life. Although visible light feels central to our experience, it represents only a small fraction of the photons that exist around us. The universe is filled with photons our eyes never detect, moving quietly through space and matter at every moment. Photons span a wide range of energies. Below visible light are infrared photons which carry less energy. These photons are closely associated with heat. Every warm object emits infrared radiation, including your body, the walls around you, and the ground beneath your feet. Even in complete darkness, infrared photons are constantly being emitted and absorbed. At even lower energies are microwaves and radio waves. These photons have long wavelengths and low frequencies. They are produced by natural processes like lightning and cosmic phenomena, as well as by human technology. Radio communication works by controlling the emission and reception of these low-energy photons. Above visible light are ultraviolet photons. These carry more energy and can trigger chemical changes. Sunburn, for example, is the result of ultraviolet photons interacting with molecules in skin cells. Beyond ultraviolet are X-rays and gamma rays, which have even higher energies and are capable of penetrating deep into matter. Despite their differences, all of these photons share the same fundamental nature. They are all excitations of the same electromagnetic field. They differ only in energy, frequency, and how they interact with matter. This uniformity is important. It means that light, heat, radio signals, and high-energy radiation are not separate phenomena. They are expressions of the same underlying structure, observed under different conditions. Our senses give us a narrow window into this spectrum. Vision evolved to detect a range of photon energies that are useful for survival on Earth's surface. But physics is not limited by biology. Instruments allow us to detect photons across the full spectrum, revealing a universe far richer than what we can see. This also means that photons are constantly interacting with us in ways we don't notice. Infrared photons from the environment help regulate body temperature. Radio photons pass through us without effect. Cosmic photons from distant sources arrive silently and unnoticed. Understanding this broad spectrum helps dissolve the idea that photons are rare or exotic. They're everywhere, all the time, forming a constant background of energy exchange. As we continue, we'll look more closely at how photons are connected to temperature and thermal processes, grounding these invisible interactions in everyday experience. For now, let this rest gently. The visible world is only a small slice of a much larger field of light. Temperature is something we feel instinctively, yet its connection to photons is often overlooked. At a physical level, temperature describes the average energy of motion within matter. Atoms and molecules vibrate, rotate, and move. The faster and more energetically they do so, the warmer the object is. Whenever matter has a temperature above absolute zero, it interacts with the electromagnetic field. These interactions produce photons. This process is called thermal radiation, and it happens continuously everywhere. A warm object does not need to glow visibly to emit photons. In fact, most everyday objects emit photons primarily in the infrared range. Your body, for example, emits a steady stream of infrared photons as it releases internal energy into the surrounding environment. This is not a special process. It is a natural consequence of temperature. As an object becomes hotter, the average energy of the emitted photons increases. At lower temperatures, the emitted photons are mostly infrared. As temperature rises, emission shifts toward visible light. When metal is heated enough to glow red, then white, it is because it is emitting higher energy photons in greater numbers. This relationship between temperature and photon energy is precise and predictable. It does not depend on the material alone, but on how energy is distributed among its atoms and molecules. This is why very different materials can glow with similar colors when heated to the same temperature. Thermal photons are constantly being emitted and absorbed. A room at a stable temperature is not static. Photons are flowing in and out in all directions, with emission and absorption balancing each other. This quiet exchange maintains thermal equilibrium. Understanding this helps clarify an important point. Heat is not a substance that flows from one object to another. It is energy in transit. When heat moves, it often does so via photons. Those photons carry energy away from warmer regions and deposit it in cooler ones. This process does not require contact. It works across empty space. The warmth you feel from the sun arrives as photons that have travelled millions of kilometers through vacuum. The warmth you feel near a fire arrives the same way, over much shorter distances. Photons involved in thermal radiation are no different in nature from any others. They are not special heat particles. They are ordinary photons defined by their energy and interaction with matter. As we move forward, we'll explore how light can travel without any medium at all, contrasting photon behavior with more familiar waves like sound. For now, you can let this idea rest. Temperature quietly fills the universe with photons, even in darkness. Many kinds of waves we encounter in everyday life require something to move through. Sound needs air or another material to carry vibrations. Water waves need water. Even seismic waves need solid ground. Because of this, it can feel natural to assume that light must also need a medium to travel through. But light behaves differently. Photons do not require air, water, or any material substance to exist or to move. They travel just as easily through empty space as they do through a room filled with air. This fact was surprising when it was first established, because it challenged long-standing assumptions about how waves work. The key difference lies in what is actually vibrating. Sound waves are vibrations of matter. Air molecules move back and forth, passing motion along. If there are no molecules, there is no sound. Light, however, is not a vibration of matter. It is a vibration of the electromagnetic field. Because the electromagnetic field exists everywhere, even in what we call a vacuum, light does not need a medium in the usual sense. There is nothing to remove in order to stop light from travelling. As long as the field exists, photons can propagate. This explains how sunlight reaches Earth. Between the sun and our planet is vast empty space, with almost no matter at all. Yet photons travel across this distance without difficulty, arriving with their energy intact. Historically, scientists once imagined an invisible substance filling space, meant to carry light waves. This idea was eventually abandoned because it was unnecessary. Experiments showed that light behaves exactly as expected without any such medium. The electromagnetic field itself provides everything light needs. Understanding this helps clarify the nature of photons. They are not disturbances moving through matter. They are self-sustaining patterns within a field that is already present. Nothing has to be pushed aside or shaken. It also reinforces why photons are not made of material components. A medium-based wave needs something to vibrate. A field-based wave does not. The field is the physical structure. As we continue, we'll look at what empty space really means in physics and why it is not as empty as it sounds. For now, let this idea settle calmly. Light moves freely because it does not depend on matter to exist. When we talk about light travelling through empty space, it's natural to imagine a complete absence of anything at all. But in physics, empty space is not truly empty. It has structure, properties, and measurable effects. Understanding this helps clarify how photons can exist and move where there seems to be nothing. In everyday language, a vacuum means a place with no air. In physics, a vacuum means a region with as little matter as possible. Even then, it is not a void. Fields still exist there. Space itself still has physical rules and measurable behavior. The electromagnetic field fills all of space, including regions far from stars, planets, or atoms. This field does not disappear when matter is removed. It is a fundamental feature of the universe. Because photons are excitations of this field, they do not need matter as a backdrop. This means that when a photon moves through interstellar space, it is not crossing nothingness. It is propagating through the electromagnetic field that already exists everywhere. The field provides the framework that allows energy and momentum to travel. Empty space also plays an active role in how photons behave. Even in a perfect vacuum, photons still obey precise physical laws. Their speed remains constant. Their energy remains tied to frequency. Their interactions, when they occur, remain quantized. In some situations, the properties of empty space itself can influence photons. Large-scale structure, such as the expansion of the universe, can stretch photon wavelengths over time. This does not destroy the photon, but it does change how its energy is distributed. The photon adapts to the changing geometry of space. This tells us something subtle. Photons are not isolated from their environment, even when that environment contains no matter. They're always part of a larger physical context defined by fields and space-time. Understanding empty space in this way helps remove the last traces of the idea that photons must be made of something solid. They do not need substance beneath them. They arise from and move within a physical structure that is more basic than matter. As we continue, we'll look even more closely at this underlying structure by exploring the idea of the vacuum in quantum physics. For now, you can let this idea rest quietly. Empty space is active, and photons belong naturally within it. To go a little deeper into what empty space really is, we need to introduce the idea of quantum fields. This can sound abstract at first, but the core idea is steady and grounded. In modern physics, fields are not things added on top of space. They are part of what space is. Every type of fundamental particle is associated with a field that exists everywhere. The electromagnetic field is one of these. Even in regions with no matter, no light, and no radiation passing through, the field is still present. It does not switch off. It does not thin out. It simply exists. The vacuum, in this sense, is not a state of nothingness. It is the lowest energy state of all these fields. There are no photons travelling through it, but the electromagnetic field itself remains. This is why a photon can be created at any location in space. The field is already there, ready to support that excitation. In quantum physics, fields do not sit perfectly still, even in their lowest energy state. They exhibit tiny fluctuations. These fluctuations are not particles popping in and out of existence in a literal way. They are small, measurable effects that arise from the uncertainty built into quantum systems. What matters for our understanding of photons is this: the vacuum is active, structured, and physical. It is not an empty stage waiting for particles to arrive. It is the underlying fabric from which particles and photons emerge. When a photon exists, it is a specific change in the electromagnetic field relative to this vacuum state. When no photons are present, the field is still there, just unexcited. This is similar to how the surface of a lake exists even when there are no waves. The water is still present even when it is calm. This view helps clarify why photons are considered fundamental. They are not objects placed into space. They are temporary, quantized patterns of activity within a field that already fills space. It also explains why we do not ask what a wave on water is made of. We understand that the wave is a motion of the water itself. In the same way, a photon is a motion of the electromagnetic field. There is no additional substance to identify. Understanding the vacuum this way also helps unify many ideas in physics. Matter particles, force-carrying particles, and photons all arise from fields. The universe is less like a collection of tiny objects and more like a set of interacting fields, continuously active even in their quietest states. As we move on, we'll look at a term that often causes confusion: virtual photons. We'll approach it carefully without exaggeration and place it properly within this field-based picture. For now, let this idea rest. The vacuum is not empty, and photons are expressions of fields within it. At this point, it's helpful to address a term that often appears in discussions about photons and fields and that can easily be misunderstood: virtual photons. The word itself can suggest something mysterious or unreal, but in physics, it has a very specific and limited meaning. Virtual photons are not particles flying around in space. They are not hidden photons waiting to be detected. Instead, they are mathematical elements used in calculations that describe how electromagnetic interactions occur. When two electric charges influence each other, when they attract or repel, we describe that interaction using the electromagnetic field. In quantum theory, this interaction can be calculated by breaking it down into exchanges of energy and momentum within the field. Virtual photons appear in these calculations as a way to represent that exchange. They are called virtual because they are not directly observable. They do not exist as free, traveling photons that could be detected by a sensor. They do not obey the same energy-momentum relationships as real photons. They are internal bookkeeping devices within the mathematics. This distinction is important. Real photons are the ones we've been discussing so far. They are emitted, they travel through space, and they can be absorbed. They carry energy that can be measured directly. Virtual photons do none of these things on their own. Using the language of virtual photons allows physicists to calculate forces with remarkable accuracy. But it does not mean that forces are literally caused by streams of tiny particles bouncing back and forth. The underlying reality is still the electromagnetic field interacting with charges. Thinking of virtual photons as real objects can lead to confusion. It can make it seem as though empty space is filled with particles constantly appearing and disappearing. That picture is not necessary and not especially accurate. What is real is the field and its ability to mediate interactions. So when you hear that forces are carried by virtual photons, it's best to translate that into calmer language. It means that the electromagnetic field allows energy and momentum to be exchanged in a way that can be calculated using quantum methods. This careful framing keeps our understanding grounded. Photons that we detect are real excitations of the field. Virtual photons are tools used to describe how the field behaves when matter interacts. As we continue, we'll return to more directly observable properties of photons, focusing next on how photons participate in forces and interactions more broadly. For now, you can let this idea settle quietly. Virtual photons are part of our descriptions, not additional things filling space. With virtual photons placed carefully in context, we can now look at the broader role photons play in forces, specifically the electromagnetic force. This force is responsible for many of the interactions we experience every day, from electricity and magnetism to the structure of atoms and molecules. At the most basic level, the electromagnetic force governs how charged particles influence one another. Electrons repel other electrons. Protons repel protons. Opposite charges attract. These behaviors are not separate from photons. They are deeply connected to the electromagnetic field that photons arise from. In classical physics, these forces are described using electric and magnetic fields that extend through space. A charged particle alters the field around it, and another charged particle responds to that altered field. The force is not transmitted instantaneously. Changes in the field propagate outward at the speed of light. In quantum physics, this same process is described using the language of photons. The electromagnetic field mediates interactions, and the exchange of energy and momentum within that field can be calculated using photon-based models. Real photons appear when energy is radiated away. Virtual photons appear inside the calculations of force. What matters for our understanding is that photons are inseparable from electromagnetic interaction. Light, radio waves, static electricity, and magnetism are all expressions of the same underlying structure. Photons are not an added feature. They are how this structure behaves when energy moves or is exchanged. This also explains why photons themselves do not carry electric charge. If they did, they would interact with the electromagnetic field in a way that would destabilize the entire framework. Instead, photons respond to the structure of space-time and fields, but they do not act as sources of the electromagnetic field. Because of this, photons can pass through one another without interference. Two beams of light can cross paths without scattering. Their fields add together, but the photons themselves do not collide or stick. This behavior follows naturally from their role as force carriers rather than force sources. Understanding photons in this way unifies many ideas. Light is not separate from electricity. Magnetism is not a different phenomenon. They are all aspects of the same field-based interaction, revealed under different conditions. As we continue, we'll look at one of the intrinsic properties of photons that plays a role in these interactions, a property called spin. For now, you can rest with this steady idea. Photons are how electromagnetic forces move through the universe, quietly and precisely. As we look more closely at the role photons play in electromagnetic interactions, an important question naturally arises. If photons are so closely tied to electric and magnetic forces, why don't photons themselves carry electric charge? The answer begins with balance and consistency in physical laws. Electric charge is what creates and responds to electromagnetic fields. If photons carried charge, they would interact with the electromagnetic field in a self-reinforcing way. Light would bend light. Beams would scatter uncontrollably. The behavior of electromagnetic interactions would be radically different from what we observe. Instead, photons are electrically neutral. They do not create electric fields of their own. They do not experience electric forces in the way charged particles do. This neutrality allows them to act as stable messengers within the electromagnetic field, rather than as sources of that field. This neutrality is not an arbitrary choice. It follows naturally from how the electromagnetic field is structured. Charged particles couple to the field in a way that produces forces. Photons are excitations of the field itself. They are part of the field's activity, not external agents acting upon it. Because photons have no charge, they can move freely through electric and magnetic environments without being deflected in the way charged particles are. A strong electric field can accelerate an electron, but it does not push a photon off course. The photon continues along its path unless space-time itself is curved or the photon interacts with matter. This distinction helps explain why light can pass through regions filled with electric fields without disturbance. It also explains why light beams do not attract or repel one another under normal conditions. Photons do not respond directly to electromagnetic forces because they are already part of the system that defines those forces. There are rare and subtle quantum effects where photons can influence one another indirectly through complex processes, but these are extremely weak and only noticeable under extreme conditions. For all practical purposes, photons remain neutral and non-interacting with each other. This neutrality is essential to the clarity of electromagnetic communication. Signals remain clean. Light travels in straight lines through empty space. Information carried by photons remains stable over enormous distances. So when we say photons carry energy and momentum but no charge, we are describing a carefully balanced role. They transmit influence without becoming sources of additional force. As we move forward, we'll examine another intrinsic property of photons that often causes confusion but plays an important role in how light behaves, a property known as spin. For now, you can rest with this idea. Photons influence the universe without carrying charge, allowing light to remain quiet, stable, and precise. As we continue building a clear picture of what photons are, we come to a property that sounds familiar, but means something quite different at the quantum level. This property is called spin. Despite the name, photon spin does not mean that the photon is literally rotating like a tiny ball. In quantum physics, spin is a fundamental property, much like energy or momentum. It describes how a particle or excitation behaves under rotation and how it carries angular momentum. For photons, spin is an intrinsic feature. It does not arise from internal motion or structure because photons have no internal parts. Photons always have a spin value of 1 unit, measured in a specific quantum way. This does not mean they spin once per second or once per cycle. It means they belong to a category of quantum entities that behave in a particular mathematical way when directions are changed. One way photon spin becomes physically meaningful is through polarization. When light is polarized, the electromagnetic field oscillates in a specific orientation. This orientation is directly related to the spin state of the photon. The photon's spin determines how its field vibration is aligned as it travels. There are 2 main spin states for free photons, often described as left-handed and right-handed. These terms do not imply direction in space like left or right hands. They describe how the field rotates as the photon moves forward. This rotation is subtle and not something we perceive directly, but it has measurable consequences. Spin affects how photons interact with matter. Certain materials absorb or transmit photons differently, depending on their spin orientation. This is why polarized sunglasses can reduce glare. They selectively block photons with certain polarization states. Spin also plays a role in conservation laws. When photons are emitted or absorbed, the total angular momentum of the system must remain balanced. If an atom emits a photon with a certain spin, the atom itself adjusts accordingly. These exchanges happen precisely, even though we never observe them directly. It's important to notice what spin is not. It is not evidence that photons are tiny spinning objects. It is not a clue to hidden internal structure. Instead, it is a reminder that quantum entities are defined by how they behave, not by how they look. Spin is one of the reasons photons fit so naturally into the field-based view we've been developing. Fields can carry angular momentum. When the electromagnetic field is excited in certain ways, that angular momentum appears as photon spin. This understanding keeps our picture clean. Photons are still excitations of a field. Spin is one of the ways those excitations are characterized and constrained. As we move forward, we'll see how this property leads naturally into polarization as a broader phenomenon, connecting abstract quantum behavior to practical observable effects. For now, let this idea rest quietly. Photon spin is not motion in space, but a fundamental rule shaping how light behaves. With the idea of photon spin gently in place, we can now look at polarization in a clearer, more grounded way. Polarization is not an added feature of light. It is a direct expression of how the electromagnetic field is oriented as photons move through space. When light travels, the electric and magnetic components of the electromagnetic field oscillate. These oscillations are always perpendicular to the direction of travel, but within that constraint there is freedom. The oscillations can be oriented in many different directions. Polarization describes that orientation. In unpolarized light, which is common in everyday situations, photons are emitted with many different orientations. Their field oscillations point in all possible directions perpendicular to their motion. Sunlight, for example, is largely unpolarized when it first reaches Earth. Polarized light is different. In polarized light, the field oscillations are restricted to a particular orientation or pattern. This can happen naturally or through interaction with matter. Reflection from surfaces, scattering in the atmosphere, or transmission through certain materials can all polarize light. From the photon perspective, polarization reflects the spin state of the photon and how that spin is aligned relative to its direction of motion. This is not something added to the photon later. It is an intrinsic part of how the excitation of the field is structured. One helpful thing to notice is that polarization is not about intensity or brightness. A polarized beam can be just as bright as an unpolarized one. What changes is the organization of the field, not the amount of energy being carried. Polarization becomes visible through its effects. Polarized sunglasses reduce glare because reflected light from flat surfaces is often polarized in a particular way. By blocking photons with that orientation, the glasses reduce the intensity of reflected light reaching your eyes. In science and technology, polarization is a powerful tool. It allows us to control how light interacts with materials, to encode information, and to probe the structure of matter. These applications work precisely because polarization is a real, physical property, not a subjective interpretation. Importantly, polarization does not mean photons are aligned like tiny arrows. The orientation refers to the electromagnetic field associated with the photon, not to a physical shape or direction of the photon itself. The photon remains a field excitation, defined by energy, momentum, and spin. Polarization also reinforces a theme we've returned to many times. Photons are best understood through relationships and behaviors, not through pictures of objects. Their properties describe how they interact, how they propagate, and how they influence other systems. As we continue, we'll look at how photons carry not just energy, but also information, and how this information is preserved across vast distances. For now, you can let this idea rest quietly. Polarization is the ordered orientation of light, revealing the structured nature of photon fields. Up to this point, we've focused on photons as carriers of energy and momentum, but photons also carry information. This idea sounds abstract at first, yet it is one of the most practical and observable aspects of light. Information, in physics, does not mean meaning or message. It means distinguishable physical states that can be transmitted and detected. Photons are especially well suited for this role because their properties can be precisely controlled and reliably measured. A photon's energy is one such property. Different energies correspond to different frequencies. By choosing which frequencies are emitted and when, information can be encoded. This is how radio communication works at its most basic level. A transmitter changes the pattern of emitted photons and a receiver detects those changes. Polarization provides another channel for information. Photons can be emitted with specific polarization states. A detector sensitive to polarization can distinguish between them. This allows multiple streams of information to be carried by light at the same time, without interfering. Timing is also crucial. The arrival time of photons can encode information. In digital systems, the presence or absence of photons within precise time windows represents bits of data. Modern communication relies on this principle, scaled up to enormous speeds. What makes photons especially useful for information transfer is their stability. As long as they do not interact with matter, their properties remain unchanged. A photon traveling through empty space does not lose its frequency, polarization, or internal structure. This allows information to be preserved over long distances. This is why photons are central to technologies like fiber optics. Inside an optical fiber, photons bounce and propagate with minimal loss. Information encoded at one end can be recovered accurately at the other, even over thousands of kilometers. Photons also play a role in biological information processing. Vision is a form of information transfer. Photons reflected from objects carry information about shape, color, and motion. When these photons are absorbed by the eye, that information is converted into neural signals. At a deeper level, photons allow us to learn about the universe itself. When astronomers collect light from distant stars and galaxies, they are collecting information encoded in photons. The energy distribution, polarization, and arrival patterns all reveal details about the source. This informational role does not require photons to be complex. In fact, it works because photons are simple and consistent. Their behavior follows strict rules. Those rules make them reliable messengers. It's also worth noticing what photons do not do. They do not interpret information. They do not decide what a signal means. They simply carry physical distinctions from one place to another. Meaning arises only when a system is built to respond to those distinctions. Understanding photons as carriers of information reinforces a key idea. Photons are not material objects transporting substance. They are structured transfers of physical properties. Energy, momentum, polarization, and timing move together as a coherent package. As we continue, we'll look at how this reliability makes photons central to modern technology and measurement. For now, let this idea rest gently. Photons quietly carry the details of the universe from one interaction to the next. Because photons are stable, precise carriers of energy and information, they have become central to many technologies that quietly shape daily life. These uses do not rely on exotic properties. They rely on the same basic behaviors we've been describing all along. One of the clearest examples is optical communication. In fiber optic cables, information is encoded into streams of photons and guided along transparent pathways. The photons reflect internally and move forward with very little loss. Because their energy and timing remain consistent, information can travel long distances with high reliability. Cameras and imaging sensors are another example. When photons strike a camera sensor, they are absorbed by tiny light-sensitive elements. Each absorbed photon contributes to an electrical signal. The image that forms is built from countless discrete absorption events, one photon at a time. Solar panels work by a similar principle. Photons from sunlight are absorbed by materials that convert photon energy into electrical energy. The effectiveness of this process depends on matching photon energies to the structure of the material. Again, nothing is gradual or smeared. Each photon either contributes its energy or does not. Medical technologies also rely on photons. X-ray imaging uses high-energy photons that can pass through soft tissue but are absorbed by denser materials. The resulting pattern of absorption carries information about internal structure. The photons themselves remain the same kind of entity, differing only in energy. Even simple devices like light-emitting diodes operate through controlled photon emission. When electric current flows through the device, electrons change energy levels and emit photons with specific energies. The color of the light is determined by the energy gap involved. Across all of these examples, the underlying physics is consistent. Photons are created through energy transitions, travel through fields, and are absorbed in discrete events. Technology works not by altering what photons are, but by arranging conditions that guide their creation and interaction. This consistency is what makes photon-based technology so dependable. Engineers do not need to wonder whether photons will behave differently tomorrow. Their properties are fixed by fundamental laws. Understanding this also brings us back to the original question. Technologies do not manipulate the material of photons because photons are not made of material. They manipulate energy levels, fields, and interactions. As we continue, we'll look at how photons are measured and how measurement itself fits into this picture. For now, you can let this idea settle quietly. Modern technology works because photons behave exactly as they always have. When we talk about photons, measurement plays a central role. Much of what we know about photons comes not from watching them directly, but from observing how they interact with measuring devices. Understanding this process helps clarify what measurement really means in physics. A measurement of a photon is always an interaction. A detector absorbs the photon, and in doing so, the photon transfers its energy to the device. That transfer produces a measurable signal, an electrical pulse, a chemical change, or a visible mark. There is no way to detect a photon without absorbing it. This is not a limitation of technology. It is a fundamental feature of photons. Because they are discrete units of energy, they can only be detected through complete energy transfer. The act of measurement ends the photon's existence as a traveling excitation. Because of this, we never observe photons in flight, in the same way we observe moving objects. We infer their motion from where they are created and where they are absorbed. Everything in between is described by physical laws, not direct observation. This does not make photon behavior uncertain or vague. On the contrary, the laws governing photon propagation are extremely precise. We can predict arrival times, energy distributions, and interaction probabilities with remarkable accuracy. What we cannot do is separate observation from interaction. Measurement also reveals the probabilistic nature of photon behavior. While we can calculate where a photon is likely to be detected, we cannot predict the exact outcome of a single event with certainty. This is not due to hidden variables or incomplete knowledge. It is a fundamental feature of quantum systems. Importantly, probability here does not mean randomness without structure. The probabilities are governed by strict mathematical rules. Over many measurements, patterns emerge with great reliability. Individual events vary, but the overall behavior is stable and predictable. This helps us avoid a common misunderstanding. Measurement does not create reality in a dramatic sense. Photons exist and propagate according to physical laws whether we measure them or not. Measurement simply reveals the outcome of an interaction at a specific place and time. Understanding measurement this way keeps the picture grounded. Photons are not mysterious observers waiting to be noticed. They are physical excitations that interact when conditions allow. As we move forward, we'll acknowledge the limits of what we currently know about photons without turning uncertainty into mystery. For now, let this idea rest gently. To measure a photon is to interact with it, and that interaction defines what we observe. Up to now, the picture of photons we've built is calm, consistent and well supported by experiment. Photons are excitations of the electromagnetic field. They carry energy and momentum. They move at a fixed speed, interact in discrete events, and follow precise statistical rules. Within this framework, predictions match observations with extraordinary accuracy, and yet it's important to pause and acknowledge a quiet truth of science. Understanding does not mean completeness. Even with everything we know, there are limits to how fully photons are explained. These limits are not signs of failure. They are natural boundaries of current theories. One such boundary appears when we try to unify different parts of physics. The behavior of photons is described extremely well by quantum electrodynamics, a theory that combines quantum mechanics with electromagnetism. This theory has been tested to remarkable precision. But when we try to integrate photons fully with gravity at the quantum level, the picture becomes incomplete. Photons clearly respond to gravity. Their paths bend near massive objects. Their energies shift as they move through expanding space. These effects are well described by general relativity, but a fully unified quantum description that includes both photons and gravity remains an open area of research. Another limit appears when we ask questions that go beyond measurable behavior. For example, asking what a photon is really doing between emission and absorption can push language beyond what experiments can answer. We can describe probabilities, we can describe field evolution, but we cannot assign a single, definite story to each individual photon's path without stepping outside testable science. This does not mean there is something hidden that we are failing to see. It means that nature may not provide the kind of narrative our intuition prefers. The laws describe outcomes and patterns, not internal experiences. There are also practical limits to measurement. Extremely subtle properties of photons may exist that are beyond our current ability to detect. Future experiments may refine our understanding, but they are unlikely to overturn the core picture. History suggests that new discoveries tend to deepen existing frameworks rather than replace them entirely. It's also worth noticing what has not happened. Despite decades of careful study, there is no evidence that photons are made of smaller constituents. No cracks have appeared in the idea that they are fundamental excitations of a field. This stability is itself informative. Science moves forward by testing boundaries. not by forcing certainty where none is available. With photons, we have a model that works extremely well within its domain. Where it stops, we acknowledge that stopping point calmly. This attitude is part of what keeps science grounded. We describe what can be measured. We remain open about what cannot yet be explained. We avoid filling gaps with speculation. So when we ask what photons are actually made of, the most honest answer remains steady. They are not made of parts. They are defined by properties and behavior arising from fields. Where that description ends, we do not rush ahead. As we move towards summarizing what we've learned, you can let this idea rest gently. Understanding photons means knowing both how much we know and where we stop. As we approach a clearer summary, it's helpful to gently clear away a few common ideas about photons that can quietly distort understanding. These ideas are not unreasonable. They come from everyday language and from early learning, but letting them go makes the picture simpler, not more complicated. First, photons are not tiny glowing objects. They do not have a surface, an interior, or a shape moving through space. Nothing is shining as it travels. Light appears only when photons are absorbed and energy is transferred. Between emission and absorption, there is no glow to imagine. Second, photons are not pieces of matter. They are not a form of very fine dust or substance filling the universe. They do not pile up, clump together, or take up space the way matter does. Even when many photons are present, what increases is energy flow, not material density. Third, photons are not waves made of something else. There is no hidden medium underneath, no invisible substance being shaken. The electromagnetic field itself is the physical structure, and the photon is a specific, quantized change in that field. Fourth, photons are not containers carrying energy like a box carries an object. The energy is not inside the photon. The photon is the energy, structured and constrained by physical laws. When a photon is absorbed, nothing is unpacked. The energy simply changes form. It's also important to say what photons are not in a more subtle sense. They are not mysteries waiting for a clever picture to unlock them. This difficulty in visualizing photons does not mean they are poorly understood. It means they are understood in a way that does not translate into familiar imagery. Letting go of these misconceptions does not remove wonder. It replaces confusion with clarity. Photons become simpler, quieter entities, not strange objects, but natural expressions of how energy behaves. As we move on, we'll gather what we've learned so far into a clean summary before widening the perspective again. For now, let this rest gently. Photons are less like things, and more like precise physical events. Before we widen the lens, it's helpful to pause and collect the main ideas we've been moving through, slowly and carefully, not as a conclusion, but as a moment of orientation. Photons are the fundamental units of light. They are not made of smaller pieces. There is no internal structure hidden inside them. As far as current science can tell, they are elementary excitations of the electromagnetic field. They carry energy and momentum even though they have no rest mass. This allows them to warm objects, drive chemical reactions, exert pressure, and transmit information. Their lack of mass is not an absence of reality. It is a defining feature that allows them to move at a fixed speed through empty space. Photons are not objects travelling through a medium. They are structured changes of a field that exist everywhere, including in what we call vacuum. When energy enters the electromagnetic field in a specific quantized way, a photon appears. When that energy is transferred back into matter, the photon disappears. While travelling, photons behave like waves. The electromagnetic field oscillates, spreads out, interferes, and diffracts. These wave behaviors determine where photons are likely to be detected. When interaction occurs, however, the outcome is always discrete. A photon is absorbed all at once, transferring its full energy in a single event. This is why photons are described using both wave and particle language. Not because they switch identities, but because no single description captures all aspects of their behavior. Motion and interaction require different perspectives. Photons are defined by properties rather than composition. Energy, frequency, momentum, polarization, and spin fully describe how they behave. None of these properties point to internal parts. They describe relationships and rules, not ingredients. They're electrically neutral, allowing electromagnetic interactions to remain stable and predictable. They can cross paths without disturbance. They can travel vast distances without changing their internal state, making them reliable messengers across space and time. When we ask what photons are made of, the most accurate answer is quiet and precise. They are not made of substance. They are made of structure, the structured behavior of a fundamental field. With this summary in place, we're ready to step back and look at photons in a wider context, how they connect to time, scale, life, and the history of the universe. That broader view doesn't replace what we've learned. It rests on it. For now, let these ideas settle together, forming a stable base. We're not rushing forward, we're just preparing the ground. Now we can widen the view and place photons within a much larger story, not just within laboratories or devices, but across time itself. Photons are among the most enduring travelers in the universe, carrying information from distant places and distant eras. When a star emits light, the photons that leave its surface begin a journey that can last years, centuries, or billions of years. During that time, they do not age, decay, or lose their identity. They move steadily through space, carrying the conditions of their origin with them. This means that when we observe light from a distant star or galaxy, we are not seeing it as it is now. We're seeing it as it was when those photons were emitted. Light becomes a record of the past preserved in motion. Some photons reaching Earth tonight began their journey long before life existed here. They crossed expanding space, passed through empty regions, and were only absorbed when they encountered a detector, a telescope, or an eye. Until that moment, they remained unchanged in their essential properties. This endurance makes photons unique witnesses. Matter can be altered, destroyed, or recycled. Photons, once emitted, simply continue until interaction ends them. In this way, they quietly connect different moments in cosmic history. Cosmic time also leaves its mark on photons. As the universe expands, the space photons travel through expands as well. This stretches their wavelengths, lowering their energy. The photons remain photons, but their frequencies shift. This is not a loss due to wear. It is a response to the changing geometry of space. Through this stretching, photons encode the expansion history of the universe. By measuring their energies and distributions, scientists can infer how space itself has changed over time. So photons are not just carriers of energy, they're carriers of history. Each one links a past interaction to a present observation. As we continue, we'll look at some of the oldest photons we can still detect, and what they reveal about the early universe. For now, let this idea rest gently. Photons are time travelers, connecting moments without aging along the way. Among all the photons we can detect, some are far older than any star, planet, or living thing. These photons do not come from a single object in space. They come from the early universe itself. Not long after the universe began, everything was extremely hot and dense. Matter and radiation were tightly coupled. Photons could not travel freely because they were constantly interacting with charged particles. Space was filled with light, but that light could not go anywhere. As the universe expanded and cooled, a quiet transition occurred. Electrons combined with nuclei to form neutral atoms. Once this happened, photons were no longer trapped. They were suddenly free to travel through space. The photons released at that moment are still traveling today. Over time, as the universe continued to expand, their wavelength stretched. Their energy decreased. What began as energetic light is now detected as very low energy microwave radiation. This radiation is called the cosmic microwave background. It fills the entire universe and arrives from all directions almost uniformly. These photons are not coming from distant galaxies. They're coming from the surface of the early universe itself. Each of these photons carries information about conditions at that time. Their energy distribution reveals the temperature of the universe when they were released. Tiny variations in their properties reveal small differences in density that later grew into galaxies and large-scale structure. What matters for our discussion is this. These photons have been travelling for nearly the entire history of the universe without changing their fundamental nature. They are still photons. They are still excitations of the electromagnetic field. They have not degraded or broken down. Their existence reinforces the idea that photons are not made of fragile components. If they were composite objects, we might expect them to decay over such immense timescales. Instead, they persist, adapting only in energy as space itself changes. These ancient photons also remind us that light does not belong only to stars and lamps. Light is woven into the structure of the universe from its earliest moments. Photons were present long before matter took its familiar forms. As we move forward, we'll connect photons to life on Earth and explore how these same basic entities power biological processes. For now, let this idea settle quietly. Some photons around us tonight have been travelling since the universe was young. After travelling across cosmic distances and deep time, photons also play an intimate role much closer to home. Life on Earth depends on them in direct physical ways, not symbolically, not metaphorically, but through precise molecular interactions. The most important connection is photosynthesis. Plants, algae, and certain bacteria absorb photons from sunlight and use their energy to drive chemical reactions. These reactions store energy in molecular bonds, forming the base of nearly all food chains on Earth. In this process, photons are not providing warmth or illumination. They are triggering specific transitions in molecules. When a photon with the right energy is absorbed, it changes the state of an electron within a molecule. That change sets off a cascade of reactions that convert light energy into chemical energy. Only photons within a certain energy range are useful for this. Too little energy and nothing happens. Too much, and the molecule can be damaged. This selectivity shows again how photons are defined by energy, not by material substance. Photons also help regulate biological rhythms. Light entering the eyes influences internal clocks that govern sleep, hormone release, and metabolism. These effects do not depend on seeing images. They depend on photon absorption by specialized cells sensitive to specific energies. Even vision itself is a biological response to photons. Each time a photon is absorbed in the retina, it triggers a tiny chemical change. Millions of these discrete events combine to form a continuous visual experience. The smoothness of perception, arises from large numbers, not from continuity at the smallest scale. At no point do living systems interact with the material of photons, because there is none. They interact with energy transfers governed by the electromagnetic field. Life has evolved to use these transfers efficiently and selectively. This perspective keeps the connection grounded. Photons do not give life meaning or purpose. They provide energy and information. Life responds because it is structured to do so. As we continue, we'll look at how human perception itself is shaped by photon interactions, focusing more closely on the eye and its limits. For now, let this idea rest gently. The same photons that cross galaxies also power the quiet chemistry of life. To understand photons in a human context, it helps to look closely at how our own eyes interact with them. Vision feels smooth and continuous, but at its foundation, it is built from countless individual photon events. Inside the retina are specialized cells that absorb photons. When a photon enters the eye and reaches one of these cells, it transfers its energy to a molecule. That single transfer triggers a chemical change. From there, a cascade of electrical signals begins, eventually reaching the brain. Each photon absorbed is a discrete event. The eye does not measure light as a continuous flow. It counts, in a physical sense, one interaction at a time. In very low light, this becomes especially clear. Under near-dark conditions, a single photon can be enough to trigger a detectable response. The range of photon energies the human eye can detect is narrow. We are sensitive only to a small band of the electromagnetic spectrum. This range happens to align well with the photons most abundant at Earth's surface, but it is not universal or fundamental. Other organisms see different ranges, and instruments extend far beyond our biological limits. Color perception arises because different cells respond differently to photon energies. Some are more sensitive to lower energy photons, others to higher energy ones. The brain compares these responses and constructs the experience of color. The photons themselves remain unchanged. Color exists only in the interaction. It's also important to notice what the eye does not detect. It does not sense photon direction directly. It does not track photons in motion. It responds only when absorption occurs. Everything between emission and absorption is inferred. This reinforces a core idea. Photons are not seen as objects moving through space. They are registered only when they transfer energy. Vision is a record of interactions, not of journeys. Understanding vision this way brings the abstract idea of photons back into the body. Our experience of the world is built from the same physical processes we've been describing all along. Quantized energy transfer, governed by fields and precise rules. As we move on, we'll step back again and look at patterns of light in nature more broadly, connecting individual photon events to large-scale order. For now, let this rest gently. Every moment of sight begins with a single photon giving up its energy. When we step back from individual photons and look at light on larger scales, patterns begin to appear. These patterns are not decorative. They arise directly from the consistent behavior of photons interacting with matter and fields. One of the most important patterns is the spectrum. When light from a source is spread out by energy, distinct bands appear. These bands reflect the specific energies of photons emitted or absorbed by atoms and molecules. Each element produces its own pattern, like a signature. These spectral patterns are found everywhere, in laboratory gases, in flames, in stars, and in distant galaxies. They tell us what matter is made of, how hot it is, and how it is moving. The photons themselves carry this information, encoded in their energies. Another recurring pattern is scattering. When photons interact with small particles or molecules, their paths are redirected. The blue color of the daytime sky, for example, arises because shorter wavelength photons scatter more efficiently in Earth's atmosphere. This is not a property of the sky itself, but of how photons interact with air molecules. Interference patterns are another example. When light passes through narrow openings or reflects from layered surfaces, photons produce regular bands of brightness and darkness. These patterns follow precise mathematical relationships and appear wherever wave behavior is allowed to express itself. Even shadows are patterns of photon behavior. A shadow forms where photons are blocked or redirected. The softness or sharpness of a shadow reflects how photons spread, diffract, and interact with edges. What's important to notice is that none of these patterns require photons to be complex. They arise because photons behave consistently. Their energies, directions, and probabilities follow stable rules. When large numbers of photons are involved, structure emerges naturally. These patterns allow us to study the universe without touching it. By analyzing light alone, we learn about stars, atmospheres, materials, and processes far beyond reach. Photons become a bridge between observation and understanding. As we move toward closing, we'll reflect briefly on why understanding photons matters to human knowledge as a whole, without turning that reflection into abstraction. For now, let this idea rest gently. Nature writes its patterns in light, using the same simple rules everywhere. After moving through fields, energy, time, biology, and perception, it's natural to ask why photons matter at all beyond their technical role. Not in a philosophical sense, but in a practical, grounded way. Photons matter because they connect many areas of science into a single coherent picture. Physics, chemistry, biology, astronomy, and technology all rely on the same basic photon behavior. When we understand photons clearly, these fields stop feeling separate. They become different perspectives on the same underlying processes. Photons also matter because they are among the simplest entities we know. They have no internal structure, no composition to analyze further, and yet, from this simplicity arises enormous complexity. Vision, communication, climate, and cosmic observation all depend on photon interactions. This simplicity makes photons reliable. When scientists measure light, they are working with entities whose behavior is deeply constrained. This allows precise measurement, repeatable experiments, and long-term predictions. The consistency of photons underpins much of what we trust in science. Understanding photons also helps clarify what "made of" really means in modern physics. Not everything is built from smaller parts. Some things are defined by behavior, by rules, and by structure rather than ingredients. Photons are a clear example of this shift in thinking. This understanding quietly reshapes how we view the universe. Reality is not only a collection of objects, it is a network of interactions, fields, and energy exchanges. Photons sit at the center of that network, linking events across space and time. There is no need to add meaning or symbolism here. The importance of photons is practical and measurable. They allow us to see, to measure, to communicate, and to learn. They are simple, stable, and deeply integrated into how the universe works. As we move toward the final sections, we'll gently return to the original question and allow it to settle into a calm, resolved understanding. For now, let this idea rest quietly. Photons matter because they quietly connect everything we can observe. At the beginning, we asked a very simple question. What are photons actually made of? We asked it in the same way we might ask what wood, water, or air is made of. And along the way, we discovered that this familiar way of asking has limits. Photons are not made of smaller pieces. They are not assembled from components. There is no hidden interior waiting to be revealed by more careful inspection. Instead, photons are defined by what they do and how they behave. They are discrete excitations of the electromagnetic field. They carry energy and momentum. They propagate at a fixed speed. They interact in precise quantized events. These properties are not consequences of composition. They are the definition. Seen this way, the question quietly changes. It moves from what substance are photons made of to what structure allows photons to exist at all. The answer lies in fields, in space-time, and in the rules that govern energy exchange. This does not make photons less real. It makes them more fundamental. They are not things placed into the universe. They are expressions of how the universe is organized at a basic level. Returning to the question now, there is no sense of something missing. The answer is complete in its own way, even if it does not look like answers we give for everyday objects. For now, you can let this understanding rest without effort. The question has done its work. One last adjustment can help everything settle more comfortably. Instead of thinking of photons as entities that exist independently, it can be helpful to think of light as an ongoing process. Energy moves from matter into fields. Fields carry that energy across space. Matter absorbs it again. Photons mark the steps of that process. They are the units by which change is counted. Nothing needs to persist beyond its role. A photon exists while energy is in transit. When the transfer is complete, the photon ends. This is not a failure or a loss. It is simply how processes work. Seen this way, photons feel less like objects and more like moments. Moments that are precisely defined, governed by strict rules, and repeated everywhere in the universe. This perspective removes strain from understanding. There is nothing to hold on to, nothing to picture tightly. There is only flow, structure, and interaction. As the mind follows this flow, it naturally slows. Questions loosen their grip. Explanations become background rather than focus. Light continues to move. Energy continues to shift. The universe continues its quiet exchange. We began with light, something familiar and constant, and followed it inward to its simplest description. Along the way, nothing dramatic was required. No hidden substance appeared. No final object was revealed. Instead, there was continuity. Fields existing everywhere. Energy moving in precise steps. Photons appearing when needed, disappearing when their work is done. The universe does not pause to explain itself. It simply continues, calmly, according to its structure. You do not need to hold these ideas actively now. They can fade gently, like light dimming in the evening. Understanding does not need attention to remain true. As your thoughts slow, let the steady motion of the physical world carry on without effort. Everything flows. Sleep in that motion.